Hello, everyone. On behalf of my colleagues, welcome to this month's talk from the Johns Hopkins Institute for Assured Autonomy seminar series, co-sponsored by the Computer Science Department of the Whiting School of Engineering. Each month, we'll have a talk on research topics at the intersection of assurance and autonomy. This seminar will be recorded. Today's speaker is Chuchu Fan. Dr. Fan is an assistant professor in the Department of Aeronautics and Astronautics at MIT. Before that, she was a postdoc researcher at Caltech and got her PhD from the Electrical and Computer Engineering Department at the University of Illinois at Urbana-Champaign in 2019. She earned her bachelor's degree from Tsinghua University, Department of Automation. Her group at MIT works on using rigorous mathematics, including formal methods, machine learning, and control theory for the design, analysis, and verification of safe autonomous systems. Chuchu's dissertation work, Formal Methods for Safe Autonomy, won an ACM Doctoral Dissertation Award in 2020. Today, Dr. Fan will talk about building certifiably safe and correct large-scale autonomous systems. Welcome, Chuchu. Over to you.
Thank you again. Nice to see everyone here virtually today. Let me start with sharing my screen. And are you able to see my screen now?
Yes, thank you.
Yep. Okay, great. All right. So thanks for the introduction, Ken, and it's really my pleasure to be able to present at the Institute for Assured Autonomy. I feel like this is exactly my research topic. So I'm going to talk about some of the recent progresses we have made at MIT about building certifiably safe and correct large-scale autonomy. And I have a subtitle here. Actually, what I'm really going to talk about today is some machine learning methods in safe automatic control and planning for large-scale autonomous systems. So you may wonder, when I say a large-scale autonomous system, what I mean by large-scale. I want to start with this picture here. Is actually a snapshot of a corner of the simulation environment that we have built. It's one of the future cities that we have vision to live in. If you can see those tiny white dots, these are drones, and there are thousands of such drones in the city. We can also put ground vehicles here, and they are supposed to collaboratively finish some tasks and make our life easier. And here, by large scale, I mean the city itself could have a large scale. We can have a huge amount of agents, and the task could be a large scale as well. Now, to be a little bit more specific, what we are looking at are the following challenges in large scale autonomy. Of course, control and planning are research areas that have been there for decades, and even like more than decades, maybe more than 100 years. There are a lot of amazing progresses that have been made over the past 100 years. Now, still there are still challenging problems for critical systems. When, for example, when we really have to coordinate and control a super large number of those agents, and when we have this system that has super high dimensional of state and input space, this is particularly standing out because recently there's a very good improvement and progress in vision-based systems. Now, vision-based input are of high dimension. Sorry, there's some echo for some reason. Now I don't hear that. And we could have unknown or imprecise models for the system and the environment. For the environment, it's easy to understand that it's imprecise as there are a lot of uncertainties. And honestly, we don't have a good model of uncertainty everywhere. And for systems, this is particularly getting a popular problem because of the machine learning modules, because of the vision component that we introduce, the these neural networks, for example, people treat those as black boxes. So we don't really have a very precise model of describing what's happening in the system. And as a result, we may not know everything precisely about the system. And finally, the requirement we want to have these systems to have can be complex. I will give you a few examples of what I mean by complex, but at a higher level, say I want to, for example, I want these thousands of drones to help me help us deliver packages in the city. Now, some packages may need a couple of drones. Some may need different types of drones. They cannot run out of battery. They need to know when they can be charged. And all these requirements together can be quite complex. So these are of course, this is not an exhaustive list of all the challenging problems, but these would be the challenges that we are very interested in. And in today's talk, I will show you some of the recent progresses we have made in terms of addressing some of these challenges. But still, these are open problems, and a lot more interesting results will come in the next few years. And I will always pay attention to the new progresses here. Now, when people talk about automatic control and planning, there are a variety of different approaches. And I have listed a couple of here that you may have heard about or you may have worked on. You may agree or disagree with my understanding of the limitations of these approaches, but in general, we can see that all the approaches kind of face a trade-off between scalability and assurance level. By assurance, I mean we can kind of have a guarantee or have a proof that the system will do whatever we want them to do. Now, in terms of control problems, of course, there are a lot of classical control technologies. For example, a lot of people are looking at optimal control, optimization-based control. They are sort of, it's not two separate things. It's kind of, people may use optimization-based approach to solve for optimal control problems. So these type of technologies, traditional control technologies, they can achieve very high assurance level in the sense that we actually trust whatever the result has been returned to us. We know, for example, I use my optimal control. If I can find a controller, it will give me the optimal kind of performance. And I don't have to worry about, the uncertainties in some black box based approaches. However, using these traditional based control approaches, people always struggle with scalability issues, primarily because these methods for solving the controllers or doing controller synthesis, they face exponential complexity in terms of dimension of the problems or the number of the agents. So it can really work well on a small number of agents or lower dimensional systems. But if we're looking at thousands of autonomous agents, for example, they have some difficulty of handling these problems. On the other side, reinforcement learning, RL, is a very popular approach these days. A lot of people are working on reinforcement learning, multi-agent reinforcement learning. And here I put constrained reinforcement learning because we still want some sort of assurance. We want some guarantees. So there are certain constraints on safety or performance. Now, although RL have been shown to work pretty well on larger scale problems, it can take high dimensional input, it can help play games pretty well. But people are wondering what kind of guarantees we can provide. It's still a very hot topic. I have to say that there aren't a lot of interesting theoretical results on what kind of theoretical guarantees we can provide, especially in terms of the whether those constraints are being satisfied. And there are, of course, other approaches. Again, this is not an exhaustive list. There are other approaches like model predictive control, MPC, that people use very widely across different domains. It kind of, it's better than the traditional control methods in terms of scalability, but still in terms of assurance level, there are certain things that these type of approaches cannot prove. For example, MPC is very difficult to prove the liveness properties of MPC than soundness properties. Now, what I want to introduce today is a very new idea called neural certificate-based control. I will tell you what is neural certificate, what I mean by neural certificate-based control, but at a high level, our motivation of looking at your certificate-based control is because we want to really break this tie of assurance level and scalability. We're looking for an approach that could potentially achieve both at a high, like give us a higher assurance level while being able to handle a large scale systems. And hopefully by the end of this talk, I can convince you that this is indeed a promising approach that can kind of handle some of the challenging problems that other methods are suffering. Now, let me switch to a more technical part of the talk. Neural certificate, what is certificate? What I mean by certificate function, what they are certifying. So in at the very first stage, the certificate functions we're looking at from control theory, they are functions that control theoretical people have proved to be able to show the desired property of the system can be achieved. I can give you a few examples here, and there are more than these examples, but these three are sort of mostly commonly used certificate functions in control theory to prove various properties of the system. If you have ever taken like a control class, you probably have heard some of those. A first one is a Lyapunov function. Lyapunov function is a very traditional, very classical control theory on stability of the system. It can certify that the system is stable around an equilibrium point or a fixed point. Now, if that fixed point is, for example, our aircraft is flying like at a horizontal level, and that could be a stable point. The second kind of certificate we're looking at is called a barrier function. Barrier function is exactly what that name indicates. Barrier function sort of define a barrier of an invariance. Invariance means something that doesn't change. If our invariance happen to be the safe kind of region, then we can use barrier function to prove safety. I will give you a few more concrete examples what I mean by, for example, the barrier function. And so the last one is called contraction metric. It's not as kind of popular as the previous two, but as an aero person, we really love contraction metric because it can certify the ability to track arbitrary trajectories, especially for drones and aircrafts. Like we have a desired path for the drone. Now, for example, like some disturbance, some wind can blow your drone away from the desired path. We want it to be able to get back to the original path it's supposed to track. And the contraction metric is indeed just a differentiable version of the Lyapunov function. Now, so all these different certificate functions, if we're able to find those, then we can certify the corresponding properties. And it doesn't mean that we can only choose one of them at each time. You can choose a subset of those or all of those to certify multiple properties. Now, let me give you an example using one of them, a barrier function, because barrier function is indeed the core to verify safety properties. What is a barrier function and how to find it? A barrier function is a scalar function h. So this function h take in the state information and also the observation information. I will show more concrete examples in the next few slides, but as of now, just bear with me in terms of understanding this barrier function. Barrier function will take in some state and information about the system and the environment, and it will output a scalar value. Now, we don't know what this h is, but we do know what this h should satisfy. H should satisfy three conditions. First of all, the value of h should be negative or 0 if the state is safe. And this safe can be any classifier that defines whether a system is in a safe state or unsafe state. And the value of h should be positive if the state is unsafe. Now, from the first two conditions, you can probably tell why it's called a barrier function. It's because h equals 0 defines the safety barrier. If you're on the negative side, you're safe. You're on the positive side, you're unsafe. So those kind of the reasons why h is called a barrier function. And finally, the third condition is a little bit complex, but what is really saying is the value of h along the trajectories, especially when it's getting close to the barrier, it should decrease. So if the value of h decreases, and it was negative, then it will remain negative. Then it kind of makes sure that the system is always in a safe region. So that is how this barrier function works. And this alpha function in the third condition is really just like a slack trying to tell you when you should make a turn when you are getting very close to unsafe. Now, each function, as I said, we know all the conditions that it should satisfy, but we actually do not know how each looks like. Over the past decades, people have tried to come up with different approaches to find the H function, find a barrier function. If we can find one, then we can have a safety proof for our system. Unfortunately, it's actually a quite challenging problem. People haven't really found a general method that can find H barrier function H for any type of a system. There are optimization-based control people, they use polynomials as a template and then find the right coefficients to find an H. It can work fine for a lower dimensional system, but for high dimensional system, it's really a challenge. Very fortunately, recently, there are a group of researchers from UCSD. They have shown us in one of their new RIPS paper in 2019 that both the barrier function and the control policy U, they can be represented as neural networks. And nowadays, people love neural networks as they are very expressive. And there are very well-developed tools that can help us find the correct neural networks that serve the purpose that we want. And in this case, we can model both the barrier function H and the controller policy input U as neural networks. And you may wonder, when now there are neural networks, how can we find the weights and bias terms of the neural networks? It's actually pretty straightforward. I have put here the lost term that you can use to find a neural network represented barrier function and policy. Basically, it's just a lost term that kind of encoded three conditions that I just described. So I have the same color coding for each of those terms. Now, the first term says H should be non-positive for all the states that are safe. And the lost term just says we're going to penalize the case when H is positive when X is safe. So what we are really doing is to penalize the violation of the condition. That's how we construct the lost term. You can see it's a very straightforward way. That's why we love this approach, in the sense there isn't really a lot of tricks you have to play here to be able to find this neural network barrier function. Now, if I use a graph or diagrams to describe what I just said, but really, we have two neural networks, one to represent the barrier function, the other one to represent the controller. And we sample there are different ways of sampling. Some people choose to sample in the state space. Some people choose to sample along the executions of the system. Each have its own pros and cons. If you're interested in some of the details, I'll be happy to get to those. But really, what we are doing is use this lost function that I defined at the top to jointly optimize for those two neural networks. Some people may wonder, can I have a single neural network? Yes, you can. You can have a single neural network that represents both the barrier function and the controller, as long as you have the separate output for each of these two parts. That's totally fine. So this neural network structure here, what we have used is a very simple architecture. It's a multi-layer perceptron with a pretty small scale neural network, like 2 or 3 hidden layers. But I think there are a lot of interesting things to be discovered here. Maybe one can design a more effective architecture to represent these barrier functions controllers. But what I want to tell you is the simplest architecture would just work. Now, you may wonder how it looks like if I use this approach to find a barrier function. So here I have shown 2 examples. The one in the middle is a neural control barrier function in robot navigation, and the one on the right is the neural network based barrier function in satellite control. Now, both these 2 examples, the neural network for the barrier functions, for the policies, they have exactly the same architecture, and we have the same lost term. So basically, it's just the same training approach for separate problems. And you can see that it can actually work pretty well for 2 both the two examples. For the navigation example in the middle, we have, this is a very simple navigation. There's a drone that's supposed to fly to the right bottom. So there's a black region on the right. The drone should always fly there. And the pink sort of boxes are obstacles. And the blue line here is the barrier that we have learned. Basically, if you're on one side of the barrier, you are always going to stay on one side. So we can see that the outline of the barrier kind of align very well with the outline of the obstacles. That means this drone will never collide with the obstacle. And another side is the third condition tells us the drone will only go to the darker and darker region. The value of H will decrease along the trajectory. So they will eventually reach that black region. They will eventually land there. The right-hand side, the satellite control example, is basically there is a target satellite in the middle. Of course, it's still orbiting. Here, we just change the coordinate to make sure the origin is at the target satellite. We want the other satellite to orbit around the center one. So basically, it cannot get too close to the center of center satellite. It cannot fly away. It has to stay within the ring region of the two purple circles. And also, ultimately, we want it to be stabilized around the ring region around defined by the two green circles. Now, you can see the barrier we have learned is the blue curves. And they are kind of like, first of all, it can guarantee safety very well. The orbiting satellite will never get across the center blue circle curve, and it will never get outside of the outer blue curve. And the green region, the green ring region is the darkest region. It will ultimately get stabilized there. So these are two sort of naive examples. I would say naive in the sense that that doesn't involve a lot of agents. At the beginning, I was like, I promise I will talk about something for large scale systems, but here it's just like one or two agents and executing some relatively simple tasks. But the purpose here is that I want to show you the uniform architecture actually can work across different problems. Now let's get to the next challenging problem. How would I scale it up? I want to start with a toy example. So this toy example, I have 4 vehicles here. They are all kind of ground dubbing cars dynamics. Basically, it's like the simplest dynamics people use to describe the car the self-driving car or any car that people are driving. Now, 4 cars, they are following their reference path. And I haven't put any collision avoidance controller on top of it. So they actually don't know. They don't know that they should avoid each other when they are getting close. The color of the dot of the car will change to blue if they're getting too close to each other, or they are getting too close to the bottom. Now, my question is, how can I design a collision avoidance controller that is provably correct or can prove none of the agents will have a collision? I have introduced a barrier function that can potentially work. I can design a big barrier function to make sure these 4 agents, they will never collide with each other. And this is going to be a centralized barrier function. Shall we just use this architecture that I have just introduced to handle this case? We can, and it can work. Actually, it can work pretty well, but there are several potential issues that we may face. The first one is a big centralized barrier function is hard to find because now your barrier function will really have to take in the state information of all the agents. I have 4 agents, each of 5 dimensions, so the input is a 20 dimension. That's probably okay for a neural network. But what if I want to put 4,000 agents in the environment? Then do I have to design like a 20,000 dimensional input neural network for a neural network? That's probably not desired. It's difficult to find and it's difficult to generalize. I don't want, like, even if I manage to find a barrier function for safety for 4,000 agents, what if I have 4,001? Am I supposed to introduce a new barrier function that can take like 4,001 agent? Of course, that's not most cost effective or computationally effective. So that's challenging problem number 1. Number 2, to have a centralized mechanism for safety and collision avoidance, we kind of have to have the state information of all agents. That's also very, very difficult. We can have like a motion capturing system that capture the state information of all agents in the room, but we cannot really fly thousands of drones in the room. Let's say we send all these drones to the city. Now they have to rely on some local communication module to communicate their information to some sort of server. There will be latency, and this communication may have some like drop in the package or failure in the communication sort of part. If we heavily rely on a central information of the global state information, that's not going to work very well, since that's not going to be very robust in terms of tolerating failures. And each agent, they kind of rely on like the perception module. They work locally. Each agent will have a camera or have a LiDAR. They will observe its neighborhood, and this neighborhood information will change. Like I could have 0 neighbor agents. I could have like some 20 neighboring agents. I should be able to design this certificate, safety certificate, that can work for a changing number, like quantity and permutation of the neighbors should not really change my safety certificate. So those are the 2 challenges that we face if we still just use a naive way of designing a big barrier certificate for the safety requirements. Now we propose this is a work with me and my student 2 years ago. We find this very interesting idea to handle these 2 like tricky problems. The first idea we have is, instead of finding a centralized barrier function, we can define something called a decentralized barrier function. And now the controller will also work in the decentralized way. Now, what is a decentralized barrier certificate? If I list the conditions for the decentralized barrier certificate, you can see that it's exactly the same as the centralized one, except that now each function, each control policy, and also each barrier certificate will also take not only the local state information, but also the observation. The observation is OI here. OI could be, for example, your LiDAR measurement, or could be your camera input. But basically, it's just what's around and what can be kind of sensed using your sensor, just locally. And in this way, everything is completely decentralized. We are not using any sort of centralized information here. The second, by the way, you may wonder, by decentralizing the barrier certificate, do I lose the guarantees, global safety guarantees? The answer is no. Actually, in this case, if we just take the maximum of all the decentralized barrier certificates, that big H, that is a maximum of all the decentralized ones, is a global barrier certificate. So we are not really learning a global barrier certificate, but we actually get one for free. We never trained one or never want to find one, but we will have that naturally for free, and we know it's there to guarantee the global safety of our system, but we don't have to find it. That's like a pretty nice deal here. And to handle the observation issue, the observation is time varying. Basically, the neighborhood information is going to change. In this case, we actually used a very standard trick in computer vision in terms of encoding a changing input into a fixed length input. So back in 2 years ago, when we used this, it was not a very popular approach in control and planning, but I have seen that over the past 2 years, a lot more people have started to realize the power of using a encoder to encode the changing input in control problems. And they work actually pretty well. So now it's not a kind of a secret anymore. Everyone kind of know that we can always encode our changing input like a LiDAR measurement or a camera-based input using a fixed length vector to make sure that all the input to the actual barrier certificate and to the control policy will be a fixed length vector, and it can work. Now let me show you some result here. For the toy example that I have just shown, we train the safe controller in the decentralized one in an empty space. So during training, all these vehicles are just running randomly in the empty space, and we collect data here, and we you learn just one barrier function and just one controller for all of them. So they have the same barrier function. Now, the left-hand side was the original kind of scenario. On the right-hand side, you can see how it looks for the multi-agent case. Now the agents, you can see that when they get close to each other, they kind of know how to avoid each other, but they are still able to get back to their original path. And that part is done by the contraction metric. You can also find a contraction metric to make sure they track their original path. And this is just for the toy example. We have tried to really scale it up. We trained with 8 agents. Still, the 8 agents in an empty space, they're just running around to a random location. And the result controller can be deployed on an arbitrary number of agents as long as they have the same dynamics. So I have put exactly the same controller on 30-ish agents where they are trying to form a square formation, or more than 100 agents, they are tracking their own path, and even more than thousands of agents here. So again, they have the same dynamic. That's why they can have the same barrier certificate and they can have the same controller. Some people may wonder, what if like here, all the agents have the same dynamics? Can I put agents of different dynamics? Here, the answer is yes, but each of the agent that have their own dynamics, we have to find their own control policy for them. They may be able to share the same barrier certificate, but they need to find their own control policy because their dynamics are different. So here, what I want to show is theoretically, this approach can be applied on an arbitrary number of agents. And empirically, we can also see that it performed really well here on more than 1,000 of those. 1,000 is not our limit. It's just like, it takes time to simulate thousands of agents, and we feel like 1,000 is already a pretty good number to test our environment. Similarly, we can do the same thing for the drones. Here, we have more than 1,000 drones in a relatively simple environment. Later on, in probably 3 slides, I will show you how it looks like in the kind of the city I introduced at the beginning. Again, there are more than 1,000 agents here, and we can see that they nicely avoid each other. We use 8 of the air vehicles, the quad routers, each of 12 dimensions, to train for the controller, and we deploy the same controller on all the agents. Here, we have a global proof that there won't be any collision. Now, some people may wonder what is really the thing that I have learned. You may wonder how the decentralized barrier function or barrier certificate looks like. I have plotted 2 scenarios here to give you an idea of what the thing that we have learned. So the top one is one scenario, the bottom one is another scenario. They're both ground vehicles, and the right-hand side is the corresponding barrier certificate, the decentralized barrier certificate that we have learned. Now, how to interpret these barrier certificates? It's actually if a new agent is going to insert this corner here, that's the value it will be given. If you can only observe all these agents in your neighbor, this is the value that we observe. Basically, this looks like a sign distance function, and is exactly what we want. So the barrier function will tell the controller that they should always go to the safe area. And we can see that here, the barriers that we have learned in the decentralized case actually align pretty well with all the obstacles. So it's a kind of like a sign distance function, but it's more than a sign distance function, because sign distance function won't be able to tell how the controller is going to react. But in this case, the barrier certificates will actually be able to tell the controller what they should react to be able to avoid the collisions with all the neighbors. So before I show you some of the visualization results, I want to say that I have introduced multiple kind of certificate functions, Lyapunov functions, barrier functions, the contraction metrics, and also decentralized version of those, including decentralized barrier function, decentralized Lyapunov function. They can all be learned using a very similar architecture that I have introduced. So basically, we have the neural network that represent the certificate. We have another neural network, or the same one, it depends on your choice, for the policy, and we encode this lost function using the way to penalize the violation of their conditions. Then we'll be able to find both. The certificate here learned is a really good proof that we can have to prove the desired system properties. And in a lot of the assured autonomy project, people are sort of spending a lot of effort trying to figure out what it means by a proof, how to construct a proof. And here, the certificate function, although they are neural networks, they are actually valid proofs for the corresponding property that we want. The learned policy can be used in closed loop with the plant. Now the closed loop system is verified or is certified by the certificate that we have learned. And the certificate can also help you monitor environmental changes or some system failures, help the system to adapt to the new environment or the new scenario. The certificate function can help you to iterate the policy locally in real time to be able to do some adaptation. So I'm not going to go deep into those type of work, but if you have interest, I'll be happy to point you to those references. So overall, this is the architecture of the whole scenario. If I'm going to show you some visualization result, so here, first of all, this is just the one special case of the drone testing. We put more than thousands of drones just at one corner of the city to test like how the drones will perform in a super crowded area. And we are just following the green one here. The left top one is our case, and the rest of three are popular reinforcement learning approaches. For those of you who work on reinforcement learning, you probably are very familiar with these approaches, CPO, PPO, TRPO. There are like pretty well developed methods for safe reinforcement learning or multi-agent version of the safe reinforcement learning. And if we look at the videos, you can see that really our approach is the only one that kind of the green drone can nicely avoid all the obstacles while still making some progress, even if it's so congested here. We also tried it on different scenarios. I will show you more later. So this one is a water, it's a boat. So boat is very interesting because boat has very big inertia. Now, if the boat is already pretty close to the obstacle, then it's too late to make a turn. That's probably why reinforcement learning is like kind of struggling with controlling the boat through this valley. There's, again, more than thousands of boats in this valley, and our approach kind of have a pretty good performance here. Now, these are the visualization result. How about in terms of, I want to show you some quantitative result. We have the different simulation environments on the right-hand side. We have ground vehicles, air vehicles, and boats. In each of these environments, there are 1,024 agents. And the result I'm showing here is average across all these different simulation environments. So if I plot the performance in terms of safety and task completion, safety is pretty easy. Safety means no collision in this scenario. And of course, you can encode other safety requirements like speed limit, battery level, all these things. As long as you can have a classifier to classify safe from unsafe, then it can be encoded in this framework. The task completion means although the agents are trying to avoid each other, we still want them to be able to reach their destination on time. So task completion means so originally without other obstacles, without other agents, they can reach their destination within a certain amount of time. We don't want the collision avoidance to cause a lot of delay. So if they are late by, say, 20% of their original time, we say they didn't accomplish their task. So some of the reason we want to measure task completion is also because to be very safe, you can be extremely conservative. For example, we can allow only one agent to move at a time. That's going to be very safe. But then we are going to have 1,000 times the original time for the last agent to be able to reach their destination. It's of course something that we do not want to happen. So we want to have both safety and like kind of making progress. Here we are comparing with still the three approaches that I have shown in the previous kind of slides. We can see that our approach is probably the only one that can achieve both almost 100% safety and 100% task completion. And the other approaches they may be good on one metric but not the others, or they could struggle with both. The center is the mean of all these bars, and the error bar means the standard deviation. Some folks may have questions here, like I kept saying that we are providing a very good theoretical rigorous proof behind it, but the performance is not 100%. So I want to admit it here, the performance is not 100%. It's somewhere between 96 to 100% due to a couple of reasons. First of all, still this is a learned controller, so we may not be able to learn the most perfect one. There are still some outliers here. And also another reason that we are not achieving 100% is there are indeed unconstructed uncertainty in the testing environment that we did not really include or consider in the training environment. So there are some scenarios or some uncertainties that we did not really consider in training that could cause a failure in this case. And in terms of sampling complexity, people may also wonder, do you have to really spend a lot of, collect a lot of data and spend a long time trying to find those certificates? Luckily, we don't. Actually, we only need 10% of the training samples than the other reinforcement learning approach to achieve a nearly perfect safety rate, where others, we pretty much converge to 100% safety rate at 1 million samples. But the reinforcement learning approaches kind of take 10 million, but still struggle with the safety rate. And this 1 million is sounds pretty a lot, but it's the number of samples, is not the number of trajectories. Each trajectory can have, for example, 1,000 samples, then you only need like 1,000 trajectories instead of 1 million trajectories. And we can also tolerate some model inaccuracy in the sense that the training model that we use can be a surrogate model that is learned from data. And even if that model of the system is not accurate, like we can have to have up to 20% of model error, but we can, even in this case, we have this proof showing that the barrier certificate that we learn actually work for the original system. So even if we can tolerate up to 20% of model error, but still being able to find a certifiably safe controller for the original system. Okay, another thing I feel very kind of interesting about is previously I showed these drones that there are a lot of them, but still their dynamics are kind of simple. But you may wonder, can we handle super complex dynamical systems? In this case, we actually tried our approach on a very interesting system. It's an F-16 model. Now, this is a simulation of F-16 model that is created in Simulink, but it's actually developed by the Air Force Research Lab people. So it's actually developed by the real flight engineers who really know how fighter aircraft works and how it's being designed. It's a quite complex Simulink model that has 16-dimensional state space and 4-dimensional input space. So it's a very challenging system because the state space itself is 16 dimension. If we just throw a massive sample there, the number of samples that you will need for any approach to work is going to be huge. And for this F-16, people want, like the folks from Air Force Research Lab, want to understand how to design some sort of autonomous functions like ground collision avoidance or waypoint tracking. Basically, with these functions, the F-16 should be able to accomplish some task like what you have seen in the movie of Top Gun. Pull up before it collides and also track some nice waypoints to be able to avoid obstacles and reach the target. Now, the model itself is so complex that the original controller was not performing pretty well. You can see that this video I'm showing here is a controller from the original model developed by the Air Force researchers. It's trying to track these waypoints, the red dots, but it cannot get very close to the waypoints. And these original controller were also sensitive in a sense, with some tricky perturbation, then the aircraft will lose speed. We apply our approach. We didn't do anything like fancy, but just did what I have just described on this model. And we found that our approach tracked the waypoints way more accurately and making sure it's very stable. You can see that this aircraft is now making some U-turns to be able to track a sequence of waypoints, and it's matching those waypoints very, very, very well. If we use reinforcement learning or imitation learning based approach, they actually can give us pretty interesting behavior. You can see in the first, like the first two cases, it's reinforcement learning and some imitation learning. The result learned actually asks the aircraft to swing very fast. It's definitely not a desired way, but it could be related to something called reward hacking, reinforcement learning. That probably is a way to hack the system to achieve a better reward. Some other reinforcement learning and imitation learning approaches, they can fly the aircraft relatively more stable, but it's hard for them to track the waypoints. The top right here is our sampling efficiency, sampling complexity. We actually only use 5% of the data that are used by other approaches to achieve pretty good performance. So that's pretty much like the main part of the talk I want to talk about, but there are a lot of interesting extensions here I want to briefly mention. I see that we are like sort of running towards the end of the talk. So I'm going to quickly go through some of the interesting work around the certifiably large-scale autonomy. But if you have interest, feel free to ask questions. I'll be happy to discuss more of the details here. First trial we have done is we want to understand whether certificate can be used in human behavior models. So basically here we have all these like a biker and also all the vehicles here. They are all human reaction model from traffic data. But there are people who study how to understand human reaction using imitation learning. I will show you like why, like the shortcomings of those pure imitation learning or behavior cloning based approaches. Here, we're trying to insert the decentralized bearer certificate to capture the collision avoidance intention of human in human models. Now, previously, the models I have shown are all dynamical models of vehicle. Here, the model is a data-driven model. It's a data-driven model that is learned from traffic data, but we're still trying to see whether we can use barrier function here to kind of capture some intention of the human models. Still, the setting up is very similar. Each of the agents will have a local observation. You can see some of the neighbors around. It turns out that if we insert a barrier certificate in our model, it can actually generalize to some unseen scenarios. For example, in this case, we have a car driving from right to left in this intersection, and the car is implemented with a very safe MPC-based controller. It will try to make some progress, but it will also try to avoid all the pedestrians if the pedestrians are getting too close to that. We see that if we use fixed trajectory, meaning just the data from traffic data or imitation learning, the pedestrians will kind of ignore the fact that there is a vehicle. They will have some crazy behavior because actually in training data, they have never seen a vehicle driving from the right to the left before. In our case, if we insert this barrier certificate in the human behavior model, you can see that the pedestrians are trying to make a way to the vehicles. It's kind of more realistic in a sense. This is how we would expect the pedestrian would do to a moving car. If the car is slow enough, it will try to make a way here. And we have sort of insert this barrier certificate to the data-driven model instead of using purely data-driven approach based on imitation learning. Here is a work called PScale that is a generative adversarial imitation learning for learning human behaviors. In different kind of traffic scenarios, we can see that we actually avoid all the kind of behaviors that are not reasonable, like the pedestrian will get very crowded to each other, or the bikers will kind of ride across the pedestrians or like directly hit the pedestrians. And the roundabout, the vehicles will be more kind of following the traffic rule. The rule here is the safety certificate that we have encoded. And I also want to show in the previously the simulation environments I have shown, the ground vehicles, the boats, and also the air vehicles in a more sparse environment, how it looks like if we use the neural certificate here. So now here in each of them, this video here only capture like a corner of the whole scenario, but there are 1,024 agents in each of this environment. They are all using the same algorithm. So it's the same architecture that is used to find a safe controller for each of the vehicle here. In all these environments, the vehicles are running the same collision avoidance controller. Of course, the controllers are different if for a car versus a drone, but you can use the same learning approach to find those. And we also tried to show how the neural certificate behaves on hardware. There are a few examples here. I can quickly show them. These scenarios are different tasks for the robots. For example, the first one I'm showing here is 2 robots trying to push a box to a desired location. It doesn't know the weight of the box, it doesn't know the friction, and you can see that some person is here actually doing a very adversarial job, is trying to poke the box away from the original path, but we want to have the guarantee that the 2 robots will always be able to push the box, and the parameters for the robots are the most robust one. By the way, all the controllers and certificates here, they're all trained in simulation. We don't have to do any hardware training. We directly train in simulation and deploy these controllers on hardware. For an ARM, if we insert a certificate, you can see that the arm will react much smoother to a load that exceeds its maximum payload. So basically, we give a payload that is heavier than what the arm can hold, but we don't want to see the arm to change dramatically. That could possibly break some hardware part of the arm. And in terms of robot navigation here on the right top, if there is a person that's trying to maliciously block the robot from going to its destination. On the right-hand side of the scenario here, you can see that if we use traditional SLAM-based state estimation plus planning, you can actually track the robot there. It needs a little bit time to get it out of that deadlock. But for our case, we can prove that the agent will always reach its destination on time. It will be able to figure out a very smooth transition to handle all these sudden changes in the environment. So these are some preliminary version of the hardware experiments. We are trying to do more. And I'm sure, if I give you an update in a few months or in a year, you will see more of these hardware experiments. Now, I want to sort of end my talk by answering some commonly asked questions about neural certificates. I have been asked these questions multiple times. First of all, the certificate functions are learned from finite sample, but the certificate should hold everywhere in the state space and input space. How can we guarantee that it is true? Of course, it's a very difficult problem, I have to say. During training, what we are doing is we make the certificate condition hold robustly instead of perfectly. For example, instead of asking it to be negative, we ask it to be negative and also have some slack to 0. We ask these certificate conditions to hold robustly on the training samples. And then if we have enough sample and some continuity assumption of the system, we can prove the certificate function hold everywhere. And another approach one can take is to use the neural network verification tools to further verify that the neural certificates actually hold everywhere. But of course, I have to say that these very rigorous guarantees that we can provide to show that the certificate function hold everywhere in the state space, it can work using these approaches I have mentioned, but they face the curse of dimensionality for sure, because whenever you want to cover high dimensional space, you have to come up with enough sample to be able to say that I have covered those space. Another question I have been asked a lot is, neural certificate need model information, but reinforcement learning does not. So this comparison with reinforcement learning is not fair. I have to say that it is unfair to some extent. And really, there's no free lunch. It's not like we develop a completely new technology that can replace reinforcement learning. The improvement in our approach is indeed because of the actual information that we have introduced. It is those control theoretical information that we have introduced that can make us perform better and have a better sampling efficiency. But on the other side, as I have described previously, our model can also be learned from data. So you don't have to have a precise model information. Some model-based reinforcement learning try to learn a model. We can also learn a model, then use that surrogate model that is learned to perform everything I have just said. We can tolerate some model error here to some extent. But you can see that it's unfair, but really the improvement is because of these control theoretical, this actual information that we have brought into the training process. And I want to finish my talk quickly by saying that some people may also wonder, you're only certifying very low-level behaviors like safety, collision avoidance. Can you do more high-level behavior, certify higher-level performance? The answer is also yes. So I'm going to skip this part, but I'm going to I want to show that higher level specifications can be described using a language called temporal logic language. And we are able to certify the temporal logic behaviors. I will stop my talk with this video. So in this video is more than collision avoidance. Multiple arms are trying to assemble an object. And there are a lot of dependencies here. For example, if they are collaboratively work on Lego, they have to be able to hold the different pieces together to put them together, or if they are doing a construction, they have to make sure the order of the pieces being put there is right. These kind of requirements can be encoded as something called temporal logic specification. And our approach can actually we have this line of work that I'd be happy to talk more offline about certifying right behaviors that can satisfy temporal logic specifications. I know I'm running like really until the last minute, but I do have a few more minutes I can answer questions.
Chuchu, thanks so much for that beautiful talk. Particularly like that last slide, the robots avoiding each other. I'm not sure how that was fascinating. So we do have a couple of questions lined up here in the Q&A. And we also have our panelists who are interested in have a couple of questions lined up. Let me start with a question from Gautam Valaba, and it, I think, may have already been answered by one of your earlier slides, talking about the rigor of the safety guarantee relies on training samples fully covering all the scenarios. How does the learned barrier certificate get around the curse of dimensionality? I think you covered that one. Related, does the learned barrier function need to be regularized in some way?
Yeah, so I kind of know that people have this type of question, and I have those, hopefully that can give you some insight on how to ensure the rigor of the safety guarantee, even if it's learned. I have talked about different approaches, and to be honest, the curse of dimensionality is there. I kind of feel that the curse of dimensionality is not a trivial problem that one can claim that can be solved. I would say, like here, we really find the form of safety certificate that was not being able to discover before. Still, you have to need some more rigorous approach. Like I said, we have to have enough samples plus some continuity assumption of the system to be able to guarantee the rigor of the safety guarantee across all different scenarios. That indeed face the curse of dimensionality. Recently, we are doing something I haven't mentioned in the talk, but instead of covering the entire state space, we have a new work that's trying to cover the entire reachable state. As long as we can ensure that the guarantee hold in the reachable state and the system will never leave the reachable state, it can still serve a pretty good safety guarantee. That can help a little bit with the curse of dimensionality, but still, these approaches, when you have a super high dimensional state, it's hard to get a, it's hard to say that I can handle arbitrary high number of dimension. And another related question is that the learned certificate barrier function will be regularized in some way. I'm not entirely sure that I understand what you mean by regularized. Now, the barrier function, what do you mean by a valid barrier function? I said that as long as you have a classifier that can tell safe from unsafe, then barrier function should serve as a barrier to make sure that all the system behavior will reside, live within one side of your classifier. It will only give you the safe behavior instead of any unsafe behavior. Now, how to connect this to regularization is a very interesting problem. We do believe that the safety requirements that can be classified in general can be learned in this approach, but there are some tricky safety requirements that are cannot be easily told by a classifier. That will be some interesting problem to study. And hopefully I answer your question, but if not, feel free to send me an email or something. I'd be happy to discuss it here.
Thank you. We are out of time, but if you could quickly handle the other question that was in the Q&A. What are your threshold and objective values for safety? In other words, how safe is safe enough?
Yeah, so threshold and objective. Now, I think I have mentioned this for the last question. The objective is really like, if I have a collection of samples, there is some sort of classifier that tells me which one is safe, which one is unsafe. Then that's our objective is to be able to really create a function that can draw a barrier along those two different kind of values. That's our objective. And in terms of threshold, of course, like if you have the safety states being exactly tangent to all the unsafe, then it will be a very tricky learning problem. I have to say, with infinite amount of data, we might be able to learn that perfect barrier, but we don't have that infinite amount of data. What we usually do is to be a little bit conservative in terms of safety. Like we push the barrier for safety a little bit inward to be more safe. And that threshold can help with the learning process. That's kind of a standard technique people use in machine learning. And this threshold usually it's really of like a case by case. If we leave some threshold, it's easier for the learning process to converge. And if we're able to learn, if the loss term converge, which is usually the case, then we are able to say that on this side of the barrier, we can guarantee all behavior of the system on this side of the barrier. That's how safe it is.
Thank you. So I think our time is up. I really want to thank you, Chuchu, for joining us at the seminar. It's a fascinating topic, some wonderful work that we hope we can collaborate with in future research work with you. Thank you so much. Thanks to our panelists. Thanks to all of you who've joined us. Look forward to seeing you next month at the IAA seminar series. Good day.
Bye.